Our journey will span many millions of years. As we travel through time and space, our destination is today. Our landing zone is the mid-coast area of Maine. Together we'll explore the beaches and rock-bound shores. The surrounding waters embrace these rocks that represent our past and our future. To learn more about their history, there will be no stone left unturned.
Over a lifetime, rocks don't change much, but how we think about them, our theories about them, are constantly changing.
For 2 days in late summer, Dr. Elizabeth Wilson, adjunct professor of earth sciences at the University of Maine at Orono, led a group of interested people on a walk along the shores of Mosquito Head and Marshall Point in the town of St. George, Maine. The walk was designed to help them better understand the geology or rocks that make up this part of the coastline. These rocks are like time capsules, reaching back almost 500 million years. Rocks are like books in a library. They are filled with information just waiting to be opened and read.
I'm often asked, why should we study the Earth? We live on the Earth, so it is important to discover what makes it tick. All of our natural resources, like water and fossil fuels, come from the Earth. By studying the Earth, we can better learn to preserve the environment that has been entrusted to all of us.
You'll never know what you'll find under a rock, someone said. But how about looking at the rock itself? You may be holding something that is 400 to 500 million years old. This program will give you the keys to unlock the secrets of these rocks that have been here for centuries, just waiting for you.
At Mosquito Head, we have all three major rock types: metamorphic, igneous, and sedimentary.
The metamorphic rocks, or country rocks as they're sometimes called, are the oldest at 500 million years. Metamorphism means just to change something, whereas igneous rocks are actually melted. Here on the coast of Maine, both granite and basalt were formed from a large blob of molten rock, deep in the earth called a pluton. The mixing of granite and basalt, two different types of igneous rock, is unusual and very exciting. Their age is around 400 million years and attracts scientists from all over the world. The sedimentary rocks were deposited during the Ice Age. This began about 2 million years ago. Today they continue to form our beaches and marshes. This time is also called the Pleistocene. Professor Wilson continues our journey from the Herring Gut Learning Center in Port Clyde, Maine. She begins with a detailed explanation of the map.
So this map comes from a geologist with the U.S. Geological Survey. And the metamorphic rocks that we are looking at are the rocks in blue.
The areas marked in red are igneous plutons.
This is the Spruce Head Pluton. Here's the Waldeboro Pluton. There's Rockland. Vinyl Haven, which is my favorite Pluton, is right there. And then I talked about this Norumbega Fault, and that's this right here. So it's just, it goes basically through Bangor and then down along the coast near Portland. And then actually they think they can trace it as far south as Connecticut, offshore in Connecticut. But so this is all the rocks we're talking about, this stuff right here. The stuff on the other side, which is most of Maine, is a totally different geologic environment. So these blue rocks, the metamorphic rocks, are the ones that may be part of some of these microcontinents that were in a proto-Atlantic environment, and perhaps are more related to Europe and Africa than they are to the other rocks in America. Here we are, the Nova Scotia and the Gulf of Maine, Avalonia. So these rocks up here are different than most of the rocks in the Appalachian system, which are these here. So this right here is, are these microcontinents. And so you can see these rocks traced up into Ireland, the UK, Wales in particular. And then perhaps some of these rocks, particularly down east in Canada, in New Brunswick, could be related to Africa. And so what's the plate tectonics model for this? Well, here's a diagram of that sort of thing. So here we have these, our little microcontinents, tiny little pieces. And this might be analogous to places in Southeast Asia now, where you have different tiny continents there that are being subducted. So the Pacific plate is going underneath some of the major plates there on the rim of the Pacific. So this material was being accreted accreted is the word we use. It was coming over here and then becoming part of the major North American continent. And as it did, you see, that's when the first phase, perhaps, of this metamorphism occurred. And when you think of, again, another kind of simple way of thinking about metamorphism is think of a snowplow. And as these sediments from this particular microcontinent came against the North American craton, they were kind of plowed up. Some of them were dragged down deep, very deep, below the continental crust, and were melted, and then came up. And remember when I was talking about the magmas coming up from very, very deep in the mantle? That's the mechanism for this happening. And along this whole area, we've got faults, we've got ruptures in the Earth's crust, where this material is coming from the upper mantle and then melting portions of the continental crust, and then coming up, some of it still being buried, and some of it coming up and being true volcanoes as well. The metamorphic rock, the very first rock that was kind of the snowplow effect, is really most of the rock that we see along the coast, mid-coast area. And then here's an area when I said, again, the concept of cooked spaghetti. See, these are metamorphic rocks, but you can see this layering. And researchers think that some of this layering may be related to the original sedimentary rocks, so the shallow to deeper water rocks. The color has to do with different, maybe, depositional environments. But this stuff isn't very much deformed.
How can a geologist tell which rock is older when they're out in the field and before they get back to the laboratory? They can tell this by cross-cutting relationships.
Here, the white squiggly rock, a quartz vein, cuts across the darker metamorphic rock, so we know that the quartz was formed after the country rock.
And now you can see there's more of a swirly mess. So these are more highly metamorphosed rocks. And we have anywhere from a fairly low metamorphism to quite a high amount of metamorphism in rocks along the coast. And maybe the reason for this is because it's near this granitic pluton. So the heat of this pluton coming up into the rocks broke off chunks of it and consumed some of it, and also caused more metamorphism to occur in the rocks. So they're more complexly deformed, and maybe, and we've got, a whole lot of quartz veins that are going through that rock too.
On the first day, the group went on a field trip to Mosquito Head to examine the metamorphic rocks there.
I think this is a good point. We have various grades of metamorphism along the coast. So it can range from low-grade metamorphism to relatively high-grade metamorphism in a very short distance. And all of this has been mapped to some degree here in the Tennant's Harbor by Charlie Gadati and his associates. Again, looking at the mineralogy, you can see all the mica, sparkly material in here.
What is mica?
That's a very common metamorphic mineral. So it's formed under fairly high pressure. So it's just when we see mica, and what metamorphic rocks are, it's a change in mineralogy. So that, when those sediments were deposited, maybe you had quartz and you had, had organic material, so you take that package and then you it goes under pressure, higher pressure, bit of temperature, and the minerals change. You've got the same components, but totally different minerals occur. And one of the very common, that's why you often get this foliation that you see. That's the nature of mica. Both biotite and muscovite it's just their mineral structure. And those are ones that you find in metamorphic rocks because they're happy under those conditions. So this is the country rock. This was here, and then we had these granitic plutons that were intruded into it with these dike systems. And those plutons really were intruded at a depth of, it's estimated at 1 to 2 kilometers. So then you can think about how much erosion had to occur, at least that much, in order to expose these at the surface today, or some other sort of tectonic process that would have brought them to the surface. So consider this the country rock. This is the most common type of rock, and we'll see different types of metamorphic rocks all along the coast of Maine and into New Brunswick. And these are the ones that they associate with rocks that they see both in Northwest Africa and Scotland and Northern Europe. So each one of these granitic plutons has its own signature. And I was saying to somebody that, they weren't all in place at the same time. They have dates on them ranging from about 420 to 380 million years ago, depending on a variety of radiometric dating techniques. But when you see pink color, that has to do with the type of feldspar mineral that you have in here, and it means that there's more orthoclase. When you have a gray color, which is what we'll see around the corner, that's more plagioclase rich. And you can see it obviously in outcrop like this. You can also make thin sections of the rock and study them in a petrographic microscope, or use other geochemical techniques to determine the mineralogy of the rock. But even within the same granite, you could have some pink areas that are a bit rich, richer in the orthoclase, and then some gray areas that are richer in another feldspar. And you have different rocks behave differently as they weather and erode. For instance, we see around the corner, we'll see a lot of these rounded boulders that are, the weathered granite features.
Rocks are broken down into smaller pieces by two major types of weathering, chemical or physical.
Wind, sun, waves, especially during storms, freezing and thawing, all contribute to the breakdown of rocks into smaller pieces.
Granitic rocks often weather in big sheets. This is called spalling, and a good example of this can be seen at Mount Waldo. Some of these weathered rocks were transported long distances by the glaciers. Glacier erratics are a dramatic example. Did you know that granite from Mount Waldo was used to build Fort Knox?
Well, let's move on and see if we can find the contact between this country rock, the metamorphic rock, and the granitic dike that intruded it. So we'll go back on the path and then out to the next outcrop. Imagine this dike coming through this country rock. What it's going to do is just grab off pieces of that rock. And this is a very, very hot magma that's coming through. So it rips off chunks of it, it falls into this mix, and then some of them melt. And so you've got this, again, a very swirly mess of really what was a magma, a liquid rock, and it's taking chunks of the country rock in with it. So here's a good contact between the granite and the metamorphic rock, the country rock. And you can see the granite actually tailing out here, and probably all of it's just melting and getting mixed up. And so when you see mixtures of these rocks, you're really probably right on that edge of that dike.
Sea level was once 200 feet lower during the time of the glaciers than it is now. The light blue on this map shows where the water of Penobscot Bay is today. The dark blue is where the ocean was when the sea level was 200 feet lower. After the glacier melted and before the land rebounded from the weight of the ice, the sea level rose, changing the shoreline and going inland as far as Millinocket. The higher ground and peninsulas became islands.
The Appalachian Mountains were once extremely high. We're down to just the core of them now. And it's just that in Maine, we didn't get that much deposition. We just got everything scraped off and moved south, except for some very major eskers.
An esker is an elongate deposit of sediment left by rivers of water flowing underneath glaciers. Maine has some of the best developed eskers in the country. They trend north-south, the direction of the glacier, and many roads have been built on them.
There were 4 major glacial periods in a period of about 1.5 million years. So they did go back and forth. And then there were probably some minor ones, I'm sure, in between that.
There are signs from the Ice Age right here in St. George.
So the main thing that you see from the Ice Age is the glacial polish and striation. If you go to Mosquito Harbor at low tide, all of those lines that are kind of going in that direction are left from the glacier. So it's not these cracks. Those aren't left from the glaciers. There's another surface on it. And it's better to look in a protected area than really out on the point. You'll see better glacial striations in an area like this. So next time you're driving by, just pull over to the side of the road at low tide and you'll be able to see that. There are fewer beaches, north of Portland. The first 70-odd miles of the Maine coast have most of the beaches, and then we have what we normally just call pocket beaches here and there. But these are 2 pretty significant beaches, I think, for mid-coast Maine.
As you look along this beach, there's proof that the sea level is rising. Local residents remember when this tree was behind the dune. In just 1 generation, the shoreline has moved inland quite a distance, even here on a protected beach. The beaches and shoreline are very dynamic systems. The daily process of tides and less frequently storms moves sediment on and off the shore. When we build structures too close to the water, and especially when we disturb the dunes and bluffs, we change the sediments moving on and off the shore. This increases erosion and causes damage to our coastline.
And then on Martinsville Beach is a pretty good sandy beach. And of course it has an island, several islands, and lots of ledges offshore. So this is more protected and you get quite a bit of sand, a very natural sand beach with a dune structure and even a little back barrier, back dune swamp, cattail swamp there in marsh. Then on the other side of Mosquito Head, you have a cobble beach. And this part of the shoreline is exposed to the open Atlantic Ocean. So there's a much larger fetch, you have higher energy conditions, and much larger material found along the beach. And you can actually see beach cusps made out of the cobbles.
Marshall Point is important because Marshall Point has wonderful exposures of metamorphic and igneous rocks. The metamorphic rocks were formed under high temperature and pressure during the movement of tectonic plates. This is the theory of plate tectonics. When you look at these rocks, think about cooking spaghetti. The rocks that weren't cooked very much still show their original bedding, just like spaghetti looks stiff when it's uncooked. Other metamorphic rocks are twisted and turned like cooked spaghetti. These highly deformed rocks were closer to the heat source, the granitic pluton. The granitic pluton here at Marshall Point is one of the many found along mid-coast Maine. What makes these plutons so exciting for geologists is the granite and basalt, 2 very different types of igneous rocks, crystallized together as the pluton formed over 1 mile deep in the earth. Scientists are still debating how this happened. One theory is that the basaltic magma, rich in magnesium and iron, deep in the mantle, moved upward into the upper mantle and crust, melting rocks rich in silica.
As it comes up through the crust, that heat melts that crustal material, which is the granite, and then forms this huge granitic pluton. And then these basalts actually shoot through because they're so hot, and at that point they're less dense. They come up into the middle of this huge melted granite blob, and then they kind of settle out because as they cool, they're really denser material because of the mineralogy of it. And another analogy for this is a lava lamp. And some of you remember the original lava lamps in the 60s. Some of you may not. But they're popular again now. But it's just that denser material, and they form almost like pillows.
As the molten rock cooled, The basalt crystallized first. The granite crystallized more slowly, forming large crystals.
See how this is higher relief than the darker material? Well, this granite has quartz in it, which is the most common mineral at the Earth's surface. It's stable at the Earth's surface. It likes to be here. It's very comfortable. And it also has some of these feldspar minerals. But this darker stuff, that was formed, that came deep down in the mantle, and it likes the mantle much better. So that erodes, it weathers at the surface more easily. So you've got a differential weathering effect here, and a difference of, 1.5 inches or 2 here between that material and this. So this is weathering away into very fine-grained material, clays and fine material. Some of it goes offshore, some of it goes around the corner, perhaps to this beach. So that's the process of weathering and transportation, and then another deposition. So you can kind of look at, even though this material here is probably about 400 million years old, it's in the process of being eroded.
In the beginning, I said rocks don't change very much, but our ideas about them do. I hope you have a better understanding of the dynamics and processes that formed our Earth as we know it today, and will continue to form it.